Welcome to today's class. Today we are seeing about Introduction to Fast Fourier Transform Algorithms. Contents of today's lecture: DFT for n-point sequence, IDFT for n-point sequence, and FFT algorithm. Welcome to today's class. Today we are going to see about Introduction to Fast Fourier Transform Algorithms. Contents: DFT of n-point sequence, IDFT of n-point sequence, and FFT algorithm for 8-point sequence. Objectives: we are going to revise DFT, we are going to revise IDFT, and we are learning FFT algorithm. Discrete Fourier transform DFT. DFT provides uniformly spaced samples of the discrete time Fourier transform DTFT. DFT definition: x of k is equal to summation over n equal to 0 to n minus 1 x of n e raised to minus j 2 pi nk upon n for k equal to 0 to n minus 1, where n are number of points in the sequence. Small n is the discrete time sample at that instant. Small k is discrete frequency sample at that instant. Inverse discrete Fourier transform, that is IDFT. IDFT definition: x of n is equal to 1 upon n summation over n equal to 0 to n minus 1 x of k e raised to j 2 pi nk upon n for small n equal to 0 to n minus 1. It requires n square complex multiplies and n into n minus 1 complex additions. Fast computation: by using the symmetry and periodicity property of the complex exponential, we can write symmetry property Wn raised to k n minus n is equal to Wn raised to minus kn equal to Wn raised to kn complex conjugate. Periodicity property: Wn raised to kn is equal to Wn k into n plus n equal to Wn k plus n into n. That is, two lengths of n by 2 DFTs take less computation than one length n DFT. 2 n upon 2 square is less than n square. Thus, the algorithm which employs computational saving are collectively called fast Fourier transforms. FFT decimation in time algorithm. DFT can be defined as x of k is equal to summation over n equal to 0 to n minus 1 x of n Wn raised to nk. That is equal to summation over n even samples x of n Wn raised to nk plus summation over odd samples x of n Wn raised to nk. That is, if we are splitting the sequences in n by 2 and n by 2, we will get for even samples summation over r equal to 0 to n by 2 minus 1 x of 2r Wn raised to 2 raised to 2k plus Wn raised to k summation over r equal to 0 to n by 2 minus 1 x of 2r plus 1 Wn raised to 2 raised to rk. That comes equal to summation over r equal to 0 n by 2 minus 1 x of 2r Wn by 2 raised to rk plus Wn raised to k summation over r equal to 0 to n by 2 minus 1 x of 2r plus 1 Wn by 2 raised to rk. DIT algorithm. A result is the sum of two n by 2 length DFTs. That is, x of k equal to g of k plus Wn raised to k h of k, where g of k is n by 2 DFT of even samples and h of k is n by 2 DFT of odd samples. Then repeat decomposition of n by 2 to n by 4 DFTs, etc. So for 8-point sequence, the final decomposition is we are getting the samples which are even samples, that are x of 0, 2, 4, 6 and x of 1, 3, 5, 7. And finally we are getting the output, that is x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. The butterfly structure. Cross feed of G of k and H of k in flow graph is called a butterfly due to its shape. So this is G of k, this is H of k. We are cross feeding G of k and H of k. So after simplification, the structure that we are getting is butterfly structure. So for 8-point DIT FFT diagram, we are having the final points as x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. This is 3-stage competition, first, second and third stage. In the third stage we are getting the output x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. So finally we can summarize today's class. That is, we have seen about n-point DFT calculation, n-point IDFT, decimation in time, fast Fourier transform and how to reduce the computational complexity by using FFTs. These are the references for today's class. Thank you.